Welcome everybody in a new video. In this video I'll explain you how does electric power in continuous current works. Before I begin I would like to tell you that if you like my videos you could consider the idea of giving me a like or subscribe to my channel. It is just a little effort for you but you will help me a lot. Okay, let's begin. So, what is power? What is electric power? Well, power is just another element like all the other elements you already know that exist in a functioning electric circuit. You know, like current, like voltage, like resistance, and then there is power too. Okay, but how do we calculate power? There are three possible ways, three possible formulas, but now we'll analyze them and we'll realize that they are actually the same formula. Let's begin with the first. Power is equal to voltage multiplied for current. Okay, this is one way to calculate power. Then there is this other one. Power is equal to resistance multiplied to squared current. Okay, let's think about this. Let's analyze this. Um, if we have squared current here, what does it mean? We can write this in this other way. Power is equal to resistance multiplied for current two times, okay? This is squared current. And now if we just consider this part, resistance multiplied for current, well, it is voltage, okay? It is the first Ohm law. So this formula is still voltage multiplied for current. It's still the same, okay? Now let's look at the third one, the third formula. This one looks a bit different, okay? Looks more different, but let's analyze this. Okay, power is equal to voltage squared, okay, squared voltage divided for resistance. Okay, square voltage. What is square voltage? Is voltage multiplied for voltage. Now we can isolate this part. Okay, voltage divided for resistance. We can isolate this part and rewrite this formula in this way. Okay, now let's just apply the first Ohm law. Volt divided for resistance is current. Okay, so we can write this in this way. And we have current multiplied for voltage. As you can see, it is still the same formula. So sometimes when you, I don't know, when you read this kind of subjects in books or in some other sources, when you are studying this subject, you could find the formula of power wrote in this way, or in this way. And maybe if it is the first time you study this subject, you may panic a bit, but don't panic, because they may look different, but they are in reality just the same formula, just wrote in different ways, okay? These formulas are the same, just wrote in different ways, okay? Now, what is the unit of measure of power? The unit of measure of power is watt. Usually you write in just a double V, just a Y, okay, in this way. An example could be, how much is the power? Well, the power is 300 watts, okay? You write it in this way. Now there are other formulas here, but before telling you about these other formulas, I would like to help you understand how to calculate power with a simple example, okay? We'll just do a simple exercise just to understand how to calculate power. Let's imagine we have a very small circuit, a very simple circuit like this, just a voltage source and then a resistor, okay? A voltage source and a resistor, just this. So we have this circuit here, a voltage source and a resistor. Let's say that the voltage source has like 50 volt, okay, and the resistor has, how much it could be, 200 ohm, okay? So we have this circuit, voltage source and resistor. Well, in this circuit we will have a current flowing here in this conventional direction, okay? We will have a current flowing this way. How much is the current? What is the value of this current? Well, let's just apply the first Ohm law and calculate it. So the current is equal to the value of this voltage source divided for the value of this resistor. So I just have to do this. So basically I have to do this 50 volt divided for 200 ohm. Okay, let's calculate it. Just give me a second, I'll do it. Okay, the value of current is 0.25 ampere. Okay. Now we have the value of current here. So, what is the value of power? Well, the value of power in this case, in this very simple case, is just let's calculate. Let's use the second formula. Power is equal to resistance multiplied for squared current. Okay, let's use the second formula in this case. We can use whatever we want with the first, the third, the second formula. Okay, it's the same, but let's use the second in this case. So the resistance value is 200 ohm. Then multiplied for squared current. This is the value of current, so 0.25 ampere, and again 0.25 ampere. Okay, resistance multiplied for square currents, multiplied 2 times for currents. Okay, it's not 2 times because okay, it's squared, it's not 2 times, but this way. Okay, now let's calculate this. Just give me a second, I'll do it. 12. Okay, the value of power in this case is 12.5 watt. This is the value of power in this particular case, in this very simple case. Okay, this was just a very simple example just to understand how can we calculate power. Okay, now let's do another. No, before doing another example, I want to explain you these other formulas. Okay, another important concept we have to talk about when we talk about power is the energy. What is energy? Well, energy is equal to power multiplied for time. Okay, energy is equal to power multiplied for time. The unit of measure of energy is joule. Okay, you usually just write this letter. Okay, I don't remember how this letter is called in English, but you write this letter. Okay, or you can measure the energy in kilowatt hours. Kilowatt hours. We'll talk later about this. So you can measure energy in joule or in kilowatt hours. Usually it's more convenient to use this representation because if you use this, you will have a very long number, so it's better to use this other one when you are talking about energy in an electronics or electronic engineering field. Okay, if you're studying physics, well, it is better to use joule if you're studying just physics, but in electronic and electronic engineering, it's better to use kilowatt hours, or you will have enormous numbers. Okay, it's better to avoid this. Okay, so this formula tells us something about the concept of power, because if energy is equal to power multiplied for time, well, this means that power is equal to energy divided for time. Okay, and this tells us something very important about the concept of power. Power is how much energy I can produce in a certain time. Okay, how much energy I can produce in a certain amount of time. This is something we can describe the concept of power we are talking now in this case. Okay, so remember about these formulas. Now let's talk about the kilowatt hours. What is the kilowatt hours? Well, 1 kilowatt is 1 multiplied for 10 cubed watt. Okay, 10 elevated to 3 watt. So, and this is just 1000 watt. Okay, so this is 1 kilowatt, 1000 watt. 1 hour is equal to 3600 seconds. Okay, so what if I multiply 1 kilowatt for 1 hour? Well, I will obtain 1 kilowatt hour. I will obtain this. I multiply 1 kilowatt for 1 hour. 1 kilowatt is when 1000 watt multiplied for 3600 seconds. And what I obtain is this. 3,600,000 600,000, okay, 3,600,000 joule. This is 1 kilowatt hour. This is why it is more convenient to use kilowatt hours instead of joule, because you see 1 kilowatt hour is equal to 3,600,000 joule, okay? So yes, it is more convenient to use this. Now maybe you can ask, maybe this could be a possible question, why if I multiplied this 1 kilowatt for 1 hour, why if I multiply watts for seconds, I obtain a measure in joule, in energy? Well, it is simple. Well, you multiply power, you are multiplying here power for seconds, you multiply power for time, and you obtain energy. Let's look about the energy formula and the power formula. Power is equal to energy divided for time, okay? So if power is equal to energy divided for time, well, what happens if you multiply power for time? What happens if you multiply power for time? What will happen in this case? Let's just analyze this formula. Power is equal to energy multiplied for time, okay? So now let's rewrite this equation in another way. If power is equal to energy divided for time, I can write this in this way. Instead of power, I will write energy divided for time, because this is what power is, okay? So energy divided for time instead of power, okay? Then I multiply it for time. What will happen here? Well, I have time here and time here, so I can delete this and this, okay? I can simplify this and this, not delete. I can simplify this and this, and what I obtain is energy, okay? So this is why if I multiply power for time, I obtain a measure in energy. And energy could be represented in kilowatt hours or in joule, okay? I multiply power for time, this is the important thing. I multiply power for time and I obtain energy. And I can represent energy in this way in joule or in kilowatt hours, okay? I hope you have understood this, I hope everything is clear till now. Another thing, yes, it is important to mention this, is the joule effect. What is the joule effect? Well, basically, when you have current flowing in a resistor, this resistor will warm up, okay? The electric energy flowing through a resistor will transform it into warm, okay? So the resistor will warm up, okay? Sorry, sometimes I just, okay. Please try to understand me. English is not my language, so sometimes, okay. I have some glitch when I speak in English. So this is the joule effect. Okay. Okay, another thing that I can mention, I don't know how much you are interested in knowing this, but okay, I'll mention this too. It is the kilocalorie. What is a kilocalorie? A kilocalorie is the energy you need to bring water to 14 degrees to 15 Celsius degrees, okay? The energy you need to bring water from 14 degrees to 50 degrees to warm up the water just from 40 degrees to 50 degrees. 1 Celsius degrees in this case, 14 to 15. And this is the 1 kilocalorie, the energy you need to do this. 1 kilocalorie is equal to 4,185 joule. So 1 kilowatt hour is equal to, if I divide 1 kilowatt hour, 1 kilowatt hour is equal to 3.6 multiplied for 10 elevated to 6 divided for 1 kilocalorie in joule, and I obtain 860 kilocalorie. So 1 kilowatt hour is equal to 860 kilocalorie. Okay, if you want to make this comparison, 1 kilowatt hour is equal to 860 kilocalorie. Well, usually in electronics, I think almost you'll never use this, so I don't know how much useful is to know this, but okay. now you know it. Okay. Now let's move to the next subject. I personally, I don't think, at least if you study this subject at a basic level, like in a, I don't think it's so important maybe. I don't think you'll use this, but okay, let's move on. Now, another important, and this is a very important concept, is the efficiency. Okay, this one is really important to know. What is efficiency? Well, efficiency is the relation between absorbed power and generated power. Absorbed power and generated power. The relationship between absorbed power and generated power is the efficiency of a circuit. So what is this? Let's try to understand this, because this may be a little, I don't know, a little difficult the first time, but let's try to understand what this is. We have a circuit here, okay, a voltage source, and as you can see there are two resistors here, but the important thing now is what these two resistors represent. These are not just two resistors, okay, they are not just two resistors. Each one represent specifically something. What is this? Let's talk about this at first. This one is we can talk the users. We can call this the users, okay? Or the user, or I don't know. There are other terms used, but let's use user, okay? This one is the user. What is the user? Well, the user could be like an electrodomestic or a machine, or what you prefer. Let's imagine something here, something that needs energy, okay? This is something that needs energy, something that needs power, okay? So this is something that had to function and needs power. It could be whatever you want. Imagine whatever you want. And this other part of the circuit, this is the part of the circuit who gives energy, okay? So this is the part of the circuit who gives energy. This could be a generator, or I don't know, a generator and some cables who brings energy. This is all the part of the circuit who gives, okay? This one gives energy, and this other part receives energy. So we could use these names. We could use receivers and givers. Okay, giver, this is the giver, and this is the receiver. We can use these names, yes, they are kinda, I think they are good in their fit to represent what we want to say. What is the power absorbed? The absorbed power. In this circuit, there will be a current flowing in this way, no? Okay, conventionally, there will be a current flowing in this way. And if there will be a current flowing in this way, obviously there will be a voltage drop here. There will be a voltage drop here. Okay, let's call VL. So there will be this voltage drop here. Well, if I multiply this voltage drop, the voltage drop here on the receiver, I multiply this voltage drop for current. This is the absorbed power. Okay, the power absorbed by the user, the receiver, okay, the electrodomestic, the machine, whatever it is, okay, the power absorbed. And what is the power generated? The power generated is the value of the voltage source multiplied for current. This is the power generated, okay. Why they are not the same? In the first simple example, they were exactly the same, because, you know, in this case they were exactly the same, but this case is not real, okay? This is just a very simple example to calculate power. In reality, this one is more similar, okay? This is more similar to a real situation. So, if this is the receiver, if this is the electrodomestic that needs to work, okay, if this is the machine that needs to work, that needs power, what is this? What this resistance represent? This one exists, and this could be a problem sometime, but what is this? What is this? Well, in reality, in the pure theory, a cable does not have any resistance. In pure theory, if I have a cable, this cable has zero resistance. Also the generator, all the material which is made of, okay, all the material a voltage generator is made of, everything of this has zero resistance in pure theory, but in reality, well, it is different. Even a cable, even just a cable in reality, it has a bit of, its own resistance, okay? It opposes a very little resistance. So imagine that I'm using some long cable, no, to bring this energy here. Imagine I'm using some long cables. The longer the cables are, and the more resistance they have, okay? And this is not the resistance this is not this resistance, okay? This is the resistance of the machine, the something that has the function, okay? The resistance of the cable is not this. It's just the resistance I have in when I transport energy, okay? So you can think about this. You can think of this about like the resistance of the cable, okay? This could be interpreted in a simple way. It's not just this, but you can interpret this in a simple way as the resistance of the cables, okay? So the longer are the cable and more resistance you will have this. This represents the resistance of the giver circuit. And in reality, yes, it exists. Even the giver circuit has its own resistance in reality. So this is why the absorbed power and the generated power are not perfectly the same, are not perfectly equal, okay? Obviously, in a well-done circuit, in an optimized circuit, the power absorbed and the power generated, they should be almost the same. If they are almost the same, this means that it is a well-done circuit, but this is not always possible. Why it is not always possible? Because maybe you have to bring power at a very long distance, okay? So if you have to bring power at a very long distance, you have to use very long cables, and if you use very long cables, well, you will have more resistance in this cable, okay? So this will be bigger if you use very long cables, okay? So this is why it is not always possible to have an optimized circuit. It's not always possible. So how do I calculate efficiency? Efficiency is calculated with this very simple formula. The relationship between absorbed power and generated power. Okay, so you just divide absorbed power divided for generated power, and so you'll calculate the efficiency. As you can see, the absorbed power is equal to the voltage drop here multiplied for current, and generated power is equal to the value of the voltage source multiplied for current. Okay, so you can write this formula in this other way. Voltage drop on the receiver multiplied for current divided for value of the voltage source multiplied for current. And since there is current here and current here, you can simplify. Okay, so you can write this formula also in this other way. You can just do this and you'll calculate the efficiency of the circuit. Just the voltage drop here, okay, divided for the value of this voltage source. And you'll obtain efficiency. Usually your efficiency is a value between 0 and 1. The more closer to 1 it is, and the more it means that it is a well-done circuit, an efficient circuit. The more close to 0 it is, and the more this means that it's not really an efficient circuit, okay? You should, if it is possible, you should optimize it. And obviously it is never 0 and it is never 1. Okay, this is just possible in a pure theoretical level, but in practice it will never be 0 and it will never be 1. Okay, 1 will be a perfect circuit and 0 will be a total trash circuit. Okay, so both these possibility are not, they do not exist, okay? In reality, they don't exist. Also, you can have efficiency expressed in percentage. How do you obtain a value of efficient expressed in percentage? Well, you just multiply efficiency value for 100 and you'll obtain maybe 80%, 90%, 60%, okay? And you'll obtain the efficiency expressed in percentage. Now, we are talking about the theory. Let's just make a last example. Let's just try to make an exercise to understand better how to calculate the efficiency. Okay. We'll just do this very simple exercise, and for this video is over, I promise, okay? Okay, now we have here we have a voltage source. And then here we have the internal resistance, okay? I haven't told you this. We can call this internal resistance, okay? This is why there is a I here, internal resistance. Okay, the internal resistance of the given circuit is this. And then we have here the receiver. The receiver this is the receiver. This resistance represents the receiver. Why do we use a L? Well, I don't remember right now why do we use a L. Okay. You can use the letter you want. You can call the things in the way you want. What is important is that you understand what you are doing and what you are talking about. This is the important thing. Then the names, you can use the names. You can give them the names you prefer, the names you want. Okay, now let's give this thing some random values. Let's say that the voltage source is equal to 100 volt. Okay, let's say it has 100 volt value. Then the internal resistance, it has like I don't know, 400 or 500. Okay, 500 ohm. The internal resistance has 500 ohm, and the receiver, okay, it has like, how much it could be, 3000. Okay, 3000. Okay, 3000. Let's say 3000 ohm. Okay, so we have these values here. Let's calculate everything. Okay, so at first we have to calculate the value of current. Okay, so we have to calculate the value of current, and well, how much it is? We just have to do this plus this. Okay, so RL plus Ri. Okay, total resistance. Let's calculate the total resistance, and it is 3500 ohm. Okay, this is the total resistance. Now let's calculate the current. How much is the current? Well, the current is equal to, I will write it here because I don't like to waste too much space. The current is well, the value of the generator just divided for the total resistance. Okay, so the value of voltage source divided for the total resistance, and the value of current is 100 volt divided for 3500 ohm. Okay, I have to write it here anyway. Okay, so 100 divided for, the value of current is 0.028 ampere. So this is our current. We have our current here. Now what we have to do? We know the current, so we can calculate now the voltage drop here. We can calculate the voltage drop here. And how much is the voltage drop? Well, it is just current multiplied for this resistance. So voltage drop on the user, on the receiver, okay, is current multiplied for the resistance of the receiver circuit. So 0.028 ampere multiplied for 3000 ohm. So the voltage drop here is 85.7 volt. Okay, now we could take a short way and calculate instantly how much is the efficiency. But okay, let's take the short way first and then we'll take a longer way. Just to, you know, to try both ways, okay? So the efficiency could be calculated just in this way. We can calculate efficiency very soon in this way, and it will just be 85.7 volt divided for 100, okay? And well, it will be just 0.85, something like this, okay? This will be the value of our efficiency. This way would be, okay. But let's try the longer way now. Let's try to calculate the absorbed power and generated power, and then let's calculate this efficiency again. Maybe I could do this here, okay, so I'll not waste another page. Okay, the generated power, the absorbed power, let's do this one first. The absorbed power is equal to the voltage drop here multiplied for current. Yes, is this. Or I can also do these resistors multiplied for squared current, okay, it's the same. Or maybe I could do also like this voltage, this value of voltage drop squared, okay, this one squared, and then divided for this, okay. All the three formulas are fine. Let's just do this, okay, this time let's use this. Okay, so let's calculate this. The voltage drop is 85.7 volt, and then I multiply this for current, which is 0.028 ampere. Okay, let's do this. .39 watt. Okay, this is the absorbed power. Now let's calculate the generated power. The generated power is the value of the voltage source multiplied for current. Well, the generated power is the voltage source, it has 100 volt, and the current is still the same, 0.028 ampere. So we have to do this now, and so let's do it. 2.8. Okay, so now we have absorbed power and generated power. Okay, absorbed power, generated power. So now we can calculate the efficiency doing absorbed power divided for generated power. So 2.39 watt divided for 2.8 watt. Let's see how much is the result here. .853. Okay, a very small difference, as you can see, but okay, this difference has, when the difference is very small, it's not important, okay. Okay, now we can also calculate the efficiency in percentage. Well, how much is the efficiency in percentage? Well, I just have to do this efficiency multiplied for 100, and the result will be 0.857 multiplied for 100. Okay, so the result will be 85.7%. Okay, the circuit efficiency is 85.7%. Okay, so this circuit is efficient only at 85.7%. It's not that bad, but it could be improved. Okay, it's not that bad, but could be better. 85.7% of efficiency, okay, in this case, in this particular circuit, in this case. Well, I think for this video is enough, and oh, there's just another thing I have to say. Yes, just another thing I have to say. It is important to tell you this too. Well, what happens when I have more than one resistors, more than one receiver, okay? And I have to calculate the total power. I will not doing any exercise, I'll just tell you how you do it, okay? Imagine you have two or more, maybe three resistors in parallel, okay? R1, R2, and R3. How you calculate the total power here? Well, the first thing you do is to calculate the current, okay? You know you have to calculate the current, and how you do it, okay? You calculate the total resistance, which is R1 plus R2 plus R3 plus Ri, okay? Okay, so you calculate the total resistance and then you do this divided for the total resistance, okay? And so you obtain the current in this way. Then, at this point, you can do this. You can obtain these 3 voltage drops. Okay, you can do in 2 possible ways, okay? You can calculate the single voltage drop on each resistance, and then in this way you'll calculate the power on each resistance, okay? Or you can calculate the voltage drop on all these 3 resistance, and then you calculate the total power here, okay? But imagine you do this, you calculate the single power of each resistance. Well, in this case, the total power, the total absorbed power, okay? The total absorbed power, the power between these 2 points will be the power on the resistor 1 plus the power on the resistor 2 plus the power on the resistor 3, okay? So when they are in series, you just sum the power, this power plus this power plus this power, okay? And you have the total power. What happens when they are in parallel? Well, it's the same. It could be not easy to understand at first, but it's the same, exactly the same. If you have 3 resistors in parallel in this way, okay, if you have this situation, now what you want to do here? Well, you'll calculate the current, the total current here. To calculate the total current, you have to do this parallel. You have to calculate this parallel, and then you'll add this parallel plus this internal resistance, okay? So you, in this case, you'll do this parallel plus this internal resistance, and you will obtain a total resistance. Then you divide the value of the voltage source for the total resistance, okay? And you obtain this current still. Now what you want to do here, what you have to do here is to calculate the voltage drop on the parallel, okay? You have to calculate the voltage drop on the parallel. And to calculate the voltage drop on the parallel, you just have to multiply current for the equivalent resistors here of this parallel, okay? You have to multiply the current for the resistors of all this parallel, okay? You multiply current for all this parallel, okay? And then you'll find the voltage drop here on the parallel, okay? And since you have the voltage drop on the parallel, you know that this value is equal to the voltage drop on every single branch of the parallel, okay? Because you just have to remember the basic rules of voltage partitioner in a parallel, okay? The voltage drop on a total parallel is equal to the value of the voltage drop on each branch of this parallel, okay? So now you can calculate, okay, knowing the voltage drop on each branch, okay, since Vp is equal to VR1 is equal to VR2 and is equal to VR3, well, you can calculate the power here, and the power here, okay? You can calculate PR1, then you can calculate PR2, and you can calculate PR3, okay? So what is the, since you calculate the the power here, here, and here. What is the total absorbed power between these 2 points, A and B? What is the total absorbed power here? Well, it is like exactly like here, same way. You do it, it doesn't matter if they are in parallel, okay? This doesn't matter. You do it in the same way. The total absorbed power, okay, between these 2 points A and B, well, it is still PR1, the power here, plus the power here. Okay, PR1 plus PR2 plus PR3. Okay, you calculate it still in the exact same way, okay? So, okay, for this video it's enough. 40 minutes, wow, okay. For this video is enough. I hope you have understood everything. I hope that everything I explained you is clear enough. And if you have any question, feel free to ask me in the comments. I'll do everything possible to answer you, to clarify your, the doubts you have. But I hope everything is clear enough and you don't have any doubts. Because this means my explaining was clear enough. Okay, so now for this video we can close it here. Yes, it's enough, and I hope you liked it. I hope my way to explain is clear enough. And okay. See you in the next video.